Hello and welcome to the third video for the first lecture for week 7. As I said at the end of the last video, of the second video, this is just going to be going through a couple of questions. It's how I normally end my lectures when I do them in person. I normally solve a few problems on the whiteboard after giving you all a few moments to have a go yourselves. So I'm going to do the same thing here. So what I recommend you do is follow along with the video, but pause it while the problem is still on the screen and have a go at solving the problem yourself using the content from the lecture, the two-part videos before, or using the lecture slides, whichever you prefer, using that content to try and solve these problems, and then follow along with me once you've had a go at it. Don't just watch the video and assume you could do it the same way I'm doing it, right? It's very hard to tell in hindsight whether you would have been able to figure it out or not. So it's best to actually pause the video, have a go at it, and then see how you went. With that said, we'll jump over and we'll have a look at the first question now. So our first question is about hanging a sculpture. You'll remember from the first video we talked about a 250 kilogram sculpture being hung from a 3-meter long cylindrical steel rod. And the rod in that example was, I can't remember exactly, but a couple of centimeters in diameter, thereabouts, and it extended by a tiny amount. There was not a lot of extension given the force of the weight of the sculpture. So this question is looking at the same problem from the other side, and it says, if we're hanging that same sculpture from a 3-meter long cylindrical steel rod, what is the thinnest the rod could be without failing? We've been given the tensile strength in the question here, so we don't have to refer back to our table of data. That is 500 times 10 to the power of 6 newtons per square meter. And so we have to try and figure out what's the smallest possible rod, the thinnest possible rod we could have that is 3 meters long that will not fail. So I will jump to my document camera and we'll have a go at this one. So the situation is just like we had before. We've got a nice long rod. It is 3 meters long. We're hanging some nice sculpture from it, and that has a mass of 250 kilograms. What else have we been given? We've been given that we have the ultimate strength of steel. Right, ultimate strength is equal to 500 times 10 to the 6 newtons per square meter. And we're asked, what is the smallest rod, the thinnest rod? And of course, we're talking about a diameter or a radius, but in the question, to solve it, we're going to need to figure out the cross-sectional area, because none of our equations had that the diameter or radius in there. We just had the cross-sectional area. And of course, for a circle, that is pi r squared to give our area. So we can use, if we can find the smallest possible area, that will obviously tell us the smallest possible diameter. So all we need to do is figure out our area based on this strength, the ultimate strength here, the length and the mass. So how do we approach that? We can start by just writing out the things we do remember. So hopefully you can remember that stress is equal to force over area. And this is the ultimate strength. The ultimate strength, remember that is the highest the stress can get before it breaks. So if the stress can at most be that, and we know the force that we've got, that'll already tell us the area based just on this equation. So what we're saying is that the stress has to be less than 500 times 10 to the 6 newtons per square meter. And since the stress is equal to F over A, that's equal to that. What we get if we rearrange that, we're bringing the A up to this side and we're taking this value down to that side. So we're going to have F over this 500 term has to be less than A. And that means that our area has to be greater than whatever this value comes out to be. Sorry, I'll just move that up. It was off screen a little bit. So the area has to be greater than whatever this comes out to be. And that makes sense because we're expecting a minimum area, i.e. a value that the area has to be above. So this makes sense so far, this term, in terms of having the inequality around that way. Of course, the force we know is just going to be mg. So A has to be greater than 250 times 9.8 over our 500 times 10 to the 6. And if you've got your calculator handy, you can obviously plug those numbers in. Hopefully you get out the same value as I did. Actually, you could do that right now. You could calculate the area. But actually, I was just thinking, we already know the formula for this based on the radius, so why don't we go straight and rearrange that instead of doing a calculation here. So if A is greater than that, then we have that area is pi r squared. So we can get that the radius is going to be greater than the square root of mg over pi times our ultimate strength, or just use sigma for now because it is the stress, it's the maximum the stress can be. So we get mg over pi times our ultimate strength. So you could just plug it straight into there, or you could plug that in and calculate the smallest area and then use that to get your radius or diameter. From that, you will hopefully find that the radius or diameter, I'll go with diameter since that's what I wrote up here, diameter comes out to be 2.5 millimeters. So to hang a 250 kilogram sculpture, this steel rod only needs to be 2.5 millimeters wide, right? And that makes sense, well, it sort of makes sense, might be surprising how small it is, but remember that when we had the example earlier, the rod that was a couple of centimeters wide, it only moved a tiny, tiny amount. So it makes sense that if it only moved a tiny amount, that we could go a lot smaller before we start to move into any kind of dangerous stretching that might actually approach that ultimate strength that would break the rod. So it sort of makes sense in that viewpoint, but at the same time, it's hard to get a feel for these sorts of things. The only real way to know whether 2.5 millimeters makes sense is to have experience with real life scenarios using that, or just a lot of practice with these sorts of problems, seeing what sort of values you get out. So we'll go back to the lecture and we'll see what our next question is. If we have a 1.6 meter long steel piano wire, so still steel, same as we've been using for the last couple of examples, but obviously equations all work the same with other values for other materials. If we've got that piano wire with a diameter of 0.2 centimeters, so 2 millimeters wide, and then we tune the piano by stretching the wire, how great is the tension in the wire if it is stretched by 0.25 centimeters when tightened? So that's our question. We'll jump over to the document camera and we will have a go at solving this one. So as usual, we want to start by writing out what we know. So our original length, L0, is 1.60 meters. So you could draw a diagram. It's not particularly useful for this one. We've got that, and then it gets extended by a bit. And this bit here is obviously delta L. This bit here is our L0, and we've been told the diameter of 0.20 centimeters. So we've been told those. Diagram's not particularly useful, but just if you need the reminder, we're looking at how much it stretches. What's that delta L? Or rather, we've been told that delta L, and we're asking what the tension is. So we've got L0, we've got delta L is equal to 0.25 centimeters, which I'm immediately going to convert into meters. So 2.5 times 10 to the minus 3 meters, just because we want everything in the same units. We've got diameter is equal to 0.20 centimeters, or again, switching into meters, 2.0 times 10 to the minus 3 meters. The area we know is going to be pi r squared, which, if you're familiar, is a quarter pi d squared, right? It's just turning r into d, but because d has the half compared to the r, you've got to, sorry, it's twice as big, you've got to divide by a quarter, twice squared. 4 cancel out by the quarter. And we have been given E as well, the Young's modulus. If we hadn't been given it, we could look that up in our tables of data. 200 times 10 to the 9 newtons per square meter. And we are looking for the tension. What is the tension? And of course, the tension is just going to be our force. The force that is being subjected, that the wire is being subjected to. So that's what we're trying to figure out. We've written down what we know. Now we just have to rearrange all our equations that we already know to try and figure out what our answer is going to be. So as usual, the way I tend to approach these is I write down the equation I have that gives me the thing I want. So we know that stress is equal to force over area. So that means that my force is going to be stress times area. All right, we know the area. We don't know the stress yet. All right, so we don't know stress, so let's think about what we can put in place of that. We know stress is equal to Young's modulus times the strain. So let's put that in. That gives us force is equal to, instead of our stress, Young's modulus times strain, so E epsilon A. So now we know Young's modulus, we know the area, well, we've got our equation for the area. We don't know the strain yet, but the strain is just the ratio of length, the fractional change in length. So strain is delta L over L naught. So that gives us that our force, our tension, is equal to Young's modulus times the change in length times the area. I'm going to change my area to my formula from before now, pi d squared over 4, and also original length on the bottom. So take a moment if you need to follow through that formula, just substituting in all those different bits. Again, you can solve these problems by calculating all the steps along the way. Right? I prefer to do the algebra, to rearrange these equations and get out one single calculation to do at the end, because for me, I'm less likely to make a mistake when I'm using my calculator. But if you're not confident with these sorts of rearranging processes with this algebra, then obviously it's a good thing to practice and get proficient at, but you are perfectly valid to do this essentially the opposite way around. Take your delta L and L naught, calculate your epsilon, your strain, take your strain and then use your equation with Young's modulus to get your stress, and then take your stress and calculate that with the area that you will have already calculated to get your force, get your tension. So you are more than welcome to do it that way, but do be aware of the issue with rounding, right? If you don't keep enough significant figures while you're doing your calculations, then it can impact your result. So do be sure to write down plenty of significant figures, or even better, to store the values in your calculator as you go, rather than just writing down things rounded and ending up with a significant rounding error at the end. So that's our formula. We've got a force, we've got this equation here, and everything in it we know. We know Young's modulus, the change in length, the diameter, and the original length. And now we can just put all the values in. And if I've rearranged everything correctly, and if my previous calculations are correct, the tension comes out to be 982 newtons, or 980 newtons if we were presenting it to the correct number of significant figures. So that is the same as supporting something with a mass of around about 100 kilograms, right? That's almost 1,000 newtons, 980. 980 is obviously 100 times the acceleration due to gravity. So it's the same as supporting something that has a mass of 100 kilograms. That would result in that rod being stretched by 0.25 centimeters or 2.5 millimeters. The thing to remember though is that pianos have a whole lot of strings. So if you were designing such a piano, you would have to take the tension of every single string into account when you were designing the frame that was actually going to support those strings, because it has to be able to withstand the tension that every single one of those strings is going to be on. They will all be pulling on that frame. So you can imagine that building a sturdy, robust piano that stays in tune is quite difficult, because you have to have a frame that can absorb that, or can withstand that amount of tension and not change a whole lot in length, to allow the strings to all change in length the required amount. So there is one more question, I believe. I'll go back to the slideshow. This last question is about two blocks, two cubes. One is made of brass, one is made of granite. The brass block is 9.9 centimeters cubed, and the granite block is 10 centimeters cubed. So it's very slightly different, right? Slightly bigger, a millimeter bigger in each dimension. The bulk modulus of brass is 80 times 10 to the 9 newtons per square meter, and for granite it is 45 times 10 to the 9 newtons per square meter. By subjecting the blocks to increases in pressure, the blocks will decrease in volume. And the question is there a pressure at which the two blocks will be the same size? And if yes, what is that pressure? So the first thing to think about is the first part of the question is there a pressure where the two blocks will be the same size? What that would mean, if you just think about it for a moment without worrying about the numbers or the formulas or anything, what it would mean is that the slightly larger block would have to shrink in volume more over some given change in pressure than the slightly smaller block. It's got to catch it up. So it means that the amount of shrinking it does has to be more than the block that starts off slightly smaller. So that's the first part of the question, is to decide which one will actually shrink more. In that case, what we can do is look at the formula for bulk strain, right? So bulk strain, if you remember, was the equivalent of strain but for a volume change. So bulk strain was given by the change in pressure. We went back to pressure rather than stress since we're now dealing with 3 dimensions. It makes sense to talk about pressure. Was equal to the bulk modulus times the volumetric strain or bulk strain, which is delta V over V naught instead of delta L over L naught, which was our 2-dimensional one. We've got delta V over V naught. What we've got is that they're both going to be subjected to the same pressure, right? So this is not changing. So that's staying constant. They have different bulk moduluses, right? Yes, they've got different different original volumes, but what we're concerned with is whether one of them will change in volume more than the other one. So if we want the change in volume to be greater, that means we need it to have a smaller bulk modulus, right? So smaller B means greater delta V. So that alone means that we can have a look at our question again, and we can, sorry, I'll just share back to the original question on the slideshow. We can have a look at this and we can check right now whether or not there is even going to be a potential pressure where this happens. So we need the one that starts bigger, that needs a greater change in volume, to have a smaller bulk modulus. And you can see that granite, which is 10 centimeters, that's the larger one, it's got a bulk modulus of 45 times 10 to the 9. The brass one, which is smaller, has a bigger bulk modulus. So our larger one does have a smaller bulk modulus, so it will shrink faster than the brass one. So the first part of the question seems to be yes, we are possibly going to get a pressure at which the two blocks will be the same size. The next part of the question is to figure out what that size is, what the pressure is rather, and then obviously the size will be given by that change. So let's go back to our document camera and write out what we know. Now that we're pretty confident there will be a possible solution, let's have a look at the values. So to start with, we're going to have bulk modulus for granite is equal to 80 times 10 to the 9 newtons per square meter. The bulk modulus for, I got that around the wrong way, that's bulk modulus for brass. Bulk modulus for granite is the smaller one, 45 times 10 to the 9 newtons per square meter. The volume, no, we'll stick with length, so we'll go with length original for brass is equal to 9.9 centimeters, and the original granite length is 10 centimeters. At this point, I'll just take a moment to point out 10 centimeters is either 1 or 2 significant figures. We don't know. Same with 80. Could be 1 or 2, but we've got 45 and we've got 9.9. So I'm going to make the assumption that these are given to 2 significant figures, and those zeros are actually significant. I'll just mention that now while I'm doing the calculation and I think of it. So the question is, what pressure, what pressure will give us the same volume, same final volume? Now this is a little bit tricky in terms of a problem. It's probably beyond what you would get in our tests or exams because of the two volumes that are both changing. It's a little bit more complicated, but it's still certainly something that hopefully you can appreciate and understand the processes involved. So if we think about these values here, we've got our original lengths. So let's turn them into volumes. Again, I would often personally do this through algebra, but for now I'm just going to write some actual numbers in just so we can see what we're looking at. So the original volume for brass, the original volume for granite are just going to be these converted to meters and then cubed. So for our brass one, we get 9.703 times 10 to the minus 4 cubic meters. And for our granite one, we get 0.001, and then it'll be 0 cubic meters, right? Or obviously in scientific notation, 1.0 times 10 to the minus 3 cubic meters. So those are our two original volumes. What we're looking for then is for the change in volume to be slightly more for this one than it is for this one. We want the final volume, VF brass, to be equal to VF granite. That's what we want. And then, as I said, it does get a little bit complicated, so try and follow along. But what we are doing is we're just going to say that our final volume for brass is going to be equal to the original brass volume minus the change in volume for brass. And that has to be equal to the final granite volume, which is going to be our original granite volume minus the change in granite volume. So that's our equation there that we're trying to satisfy. We want these to be, these two sides to be equal. We already know these two values. We just calculated them. We don't know the change in volumes for either one yet, but we do know our formula that involves the bulk modulus gives our change in volume based on the change in pressure. So we can then use that, substitute in some equations there, and we get that our original brass volume minus, if you look here, delta V, if we rearrange this, the V naught and the B are going to the other side. So we get V naught delta P over B is equal to delta V. All right, so I'll just squish that in there. But that's what we're going to put in place of our delta V. V naught, change in pressure over the bulk modulus. So V naught brass, change in pressure over the bulk modulus for brass. And that's going to be equal to our original volume for granite minus original volume for granite delta P over bulk modulus for granite. So that's our formula there. As you can see, we've got delta P. I've left delta P the same. I didn't bother with the subscripts because we're saying that they are subjective to the same change in pressure. And we've now got some equations that we can rearrange. You could keep going with the algebra, or as I've said, you could put in the values and just do the calculation right now. And that is the easiest approach if you don't want to do as much algebra. So if you put in all of those values and see what you get out, according to my calculations, it comes out to be, what have we got? What we end up with is 1.009 times 10 to the minus 14 delta P is equal to 2.97 times 10 to the minus 5. So obviously I've done a bit of rearranging. So we know that value, that one, that one, that one, that one, and that one. And then I move the two delta P terms to the same side and the two original volumes to the same side. And then we end up with this resulting, which means that our delta P is just going to be this, 2.97 times 10 to the minus 5 divided by 1.009 times 10 to the minus 14. And that comes out to be 2.94 times 10 to the 9 Pascal. That is around about 3 gigapascal, right? Or 2.9, but around about 3 gigapascal. the reason I mentioned, oh, that's right off the page now, there we go, sorry, it's around about 3 gigapascal. The reason I mentioned that in terms of gigapascal is because the bottom of the Mariana Trench, if you're all familiar with that, the deepest place in the oceans on Earth, so the deepest we can possibly get by going underwater, is around about 0.1 gigapascal. Right, 0.1 gigapascal. And we just said that to change these blocks, one of them was 10 centimeters diameter, 10 centimeters cubed. The others was 9.9 centimeters in each dimension, only a millimeter difference. But for the bigger one to catch up the smaller one as they're shrinking would take 3 gigapascal of pressure. So not feasible in everyday life. So that is the end of the problems for this lecture. Hopefully you've been able to follow those along. Obviously there are some more problems listed for the textbook as well as the ones for the workshop on Friday. So we'll see you at those. You will get some more recordings for lectures 2 and 3 over the next day or two. Thank you.